So thank you, Stefano, again. And we are going to move to the next talk. And the next talk will be given by Isabel Hernandez from University of Michigan. Isabel, can you hear us?
Yeah.
Okay, so
I will share my screen.
Share your screen when you're ready, please. And the title of Isabel's talk is Characterization of FS3, a detection system for neutron-photon correlations in fission. So please start your presentation when you're ready.
Thank you. Thank you for that introduction. Good afternoon. My name is Isabel Hernandez. I am an undergraduate student fellow in NBT at the University of Michigan. And today I'm going to talk about a detection system for neutron-photon correlations in fission. To start off with, fission is a nuclear reaction or radioactive decay process where the atom splits into its daughter components. In this process, energy and particles are released, and these loose particles, typically neutrons and photons, should theoretically have some sort of relationship or correlation to each other. And in fact, we see these correlations in experiment, but they haven't really been satisfactorily described in nuclear physics theory. We also know that both in experiment and simulation, the physical system response accounts for large bias of results. To therefore determine correlations, theoretical predictions and extremely precise characterization of the system is required. The fission sphere detection system, I'll be calling it FS3, is designed to be responsive to these correlations. And by simulating the FS3 system and comparing it to experimental results, we may find the system bias and therefore sensitivity of the system to correlations. Taking a step back to look at the greater scheme of things, it's essential to characterize these correlated fission signatures because visual material and therefore special nuclear material are characterized by these observables. So by making and optimizing a detection system to look at these, we could prevent nuclear weapon proliferation and reduce the threat of nuclear and radiological terrorism, which aligns directly with the NNSA mission. The actual fission sphere is comprised of 40 organic scintillation detectors. Stefano mentioned it actually earlier in the previous presentation, 30 of which are steel beam crystals and the remaining 10 are EJ309. As you will see later on, we distinguish particles using pulse shape discrimination and time of flight techniques. The detectors have a total absolute efficiency of 15% for both neutrons and photons. On the right, you can see some visualizations of the system rendered in VisEd and in CAD. So when we say we're looking at correlations in fission products, we mean that we're specifically focusing on the relationship between neutron and gamma ray multiplicity, and then also the relationship between neutron multiplicity and average neutron energy within a single fission event. As you can see from the figure on the right, both Freya and CGMF event generators predict a negative correlation between neutron multiplicity and gamma ray multiplicity. And I'm going to talk about this later on as well. So to understand the system response or the bias of FS3, it is necessary to first simulate the experiment. So we may use this response to unfold experimental data later on. For simulation, we produced both a correlated and uncorrelated californium-252 spontaneous fission source. And we did both of these just to see how the environment bias affects both situations. To produce the correlated californium source, the fission reaction event yield algorithm, Freya, was used. Freya is a Lawrence Livermore National Laboratory physics-based event generator. On the other hand, MCMPX Polimi contains an IPOL option to generate uncorrelated fissions. Specifically, we use the IPOL1 equals 10 card, and from now on, I'm going to be referring to this generator as IPOL for less confusion. So this optional generator was then used to produce the uncorrelated californium source. Both sources, correlated and uncorrelated, were then propagated onto a model of the FS3 system by MCMPX Polimi. This slide shows the results that we got from simulation. The top two figures illustrate the correlations in Freya missions within a single fission event. As you can see, without any detectors to gather data and taking all of the simulated particles into account, there is an obvious negative correlation between neutron multiplicity and photon multiplicity. And we saw this a few slides back when comparing Freya to CGMF as well. This just kind of cemented what we already knew. FRIA shows a slightly more complex relationship between neutron multiplicity and average neutron energy within a single fission event. And it's important to note that the top two figures only show FRIA emissions. This is because we know that IPOL emissions are completely uncorrelated, so it would essentially just be a horizontal line for both figures. The bottom two figures are what the model detectors pick up in MC and PX Polimi from the events generated from FRIA and IPOL. On the bottom left, we have detecting neutron multiplicity versus detected average photon multiplicity. FRIA still has a strong negative component, but the events generated from IPOL have a slight positive correlation towards N. This leads us to believe that the system introduces a positive correlation bias, since we expected the IPOL line to be essentially horizontal. Comparing the two graphs on the bottom, we can see that the system introduces a very strong and therefore insensitive bias in multiplicity energy correlations, as you can see on the figure on the bottom right, but is more sensitive to multiplicity correlations, making FRIA and IPOL events diverge from one another. For this reason, we're just going to be concentrating on the multiplicity relationship. Once we had the results from simulation, our team was given the opportunity to test out a preliminary experiment at Oak Ridge National Laboratory. This smaller setup consisted of 6 steel beam detectors, as seen on the VisEd rendering on the right. From the data gathered from Oak Ridge, we developed a processing code to extract all of the information. As you can see in this 3D histogram figure where light output is on the x-axis and PSD, calculated by tail over total, is on the y-axis, we parsed through all of the slices for all the detectors and fitted each PSD slice. You can see an example of one of the slices in the figure to the right. We determined the discrimination line between neutrons and photons by taking the intersection between the two fits. And that intersection line is represented by the blue line on the figure on the right. This was repeated for all the bins for entries over 1,000 and for all 6 detectors in this setup. The figure on the left shows actually the same graph we saw before, but with all the discriminations for all the bins laid over top in yellow. Again, we have light output or deposited energy in MEVE on the x-axis and tail over total on the y-axis. Since photons typically deposit all of their energy in a short amount of time and arrive virtually at the same time within the detector, the tail of the photon pulse is significantly shorter than the body of the pulse. So the bottom distribution below the yellow line represents photons from fission. On the other hand, neutrons have a longer deposition period because of delayed prompt emission and scintillation neutrons. So everything above the yellow line is predicted to be neutrons. It becomes clear that as light output increases along the x-axis, the distance or the clarity between the two distributions becomes clearer, so the discrimination is more obvious. Towards the y-axis, you can see some muddling between types of particles. On top of PSD, we also use time of flight to discriminate incoming photons from neutrons. In this figure, where the x-axis is PSD or tail over total again, and the y-axis is time of flight in nanoseconds, you can see that our system provides a very clear discrimination between neutrons and photons. This is seen in the 2 clear groupings in the middle of the blue distribution. Photons should make up the left distribution where both PSD and time of flight is low, and neutrons should compose the right distribution where both PSD and time of flight is higher. These 2 groups are very isolated and serve to prove that discrimination in this setup is pretty reliable when taking time of flight into account. Just as a little side note, the time of flight is kind of unusually high for a detector this close to the source. This was because there was a delay in the system that altered measuring times. However, there were some obstacles when discriminating particles. As you can see from the figure on the left with time of flight on the x-axis and light output on the y-axis, the photon distribution on the left towards that yellow spot is very spread out. This is unexpected since photons should enter the detector at relatively the same time, and this figure shows that photons have an unusually long and varied time of flight and low energy. This could be due to scattering and other environmentals photons encountered before being tagged in the detector, but ultimately we narrowed it down to amplitude walk. This is where 2 pulses of the same shape and time of occurrence get tagged by the detector at different times because of their differing amplitudes. Even though we didn't account for amplitude walk using constant fraction discrimination, we still have a pretty accurate discrimination because of all of the methods that I just highlighted before, like time of flight, light output, and PSP. In the future, we will be calibrating our equipment to take amplitude walk into account by using CFD. Moving forward, we plan to provide a comparison between simulation and experimentally detected results for this full system array, as well as use the calculated system response to unfold experimental data and ultimately get our ultimate goal, which is the sensitivity of FS3 to correlations. We may also include angular correlations, as well as provide a Freie error analysis to determine how robust our Freie Californium dataset is to slight fluctuations of input. Personally, MTV has provided me with so many opportunities since starting my student fellowship, specifically this summer when funding me on this project. MTV also offers a summer school that has definitely helped my understanding in theoretical physics as it relates to my current project and my future aspirations. In this project specifically, we directly collaborated with Oak Ridge National Laboratory with the preliminary experiment, and as well as Lawrence Livermore National Laboratory with using and modifying their Freie open source code. MTV has also given me the chance to explore multiple national labs for internships and specifically supported me in earning an internship at Los Alamos National Laboratory this summer. Unfortunately, due to COVID-19, my plans for Los Alamos were cut, but I'm so glad that I can still contribute to MTV as a summer fellow now. MTV would like to thank the NNSA and DOE for their support in our research. Thank you for listening to my presentation, and are there any questions?
Thank you, Isabel, for that excellent talk. We enjoyed that, and it is a shame that the summer has kind of the events have come in the way of you going to those labs, but I'm sure you will have an opportunity in the future. We have time for comments. I see Ramona's hand is still raised. I presume this is from last talk. Or Ramona, do you have another question, maybe related to this talk?
Sorry about that, but maybe I could, can you go back a little bit?
Yeah.
Yeah, so, sorry, maybe down a little further. I didn't catch this slide number. Okay. Yeah, I don't know quite what to say about the detected versus emitted, but it looks like it's kind of interesting that the bottom right plot, there seems to be some stronger correlation with this. I mean, well, okay, strong and strong. It's not a very big scale, as I realize now. But it does seem like this Polimi one has pretty much the same behavior as Freie, but the one on the other side for the photon multiplicity doesn't.
Yeah, that was really interesting, and that's why we really didn't know what to do with the neutron multiplicity versus average energy. So that's why we kind of didn't focus on that one, but we could see the obvious difference in this one. So this will definitely contribute to finding the sensitivity of the system, especially when it comes to multiplicity counting. So
sure, but this energy, is that photon energy or?
Oh, for which graph? Sorry.
The ones on the right, that just says energy, but I'm not sure energy of what.
Yeah, it's neutron energy. So deposited neutron energy. Sorry about that.
So both of them are neutron energy.
Yes.
Okay. Thank you.
Yeah.
And I'll put my hand down now.
Sure. Any other questions from the audience? I have a question related to those long time of flight events, which look like photons, and you mentioned how those could result from the scatter in the environment. Is that something you can simulate, at least to see whether that's a feasible explanation with regards to just both the time of flight and the magnitude of the effect that you see?
So yes, we do find these in simulation. We just don't take them into account. So the crosstalk is never removed either. So we see them both in a simulation and an experiment. Yeah.
And the magnitudes are also comparable in the experiment and simulation of those effects.
I believe so, yes.
Okay. Well, if there are no further questions, let's